Hey guys, so in this video I want to introduce you to the idea of elastic potential energy. Now we've already talked about kinetic energy and gravitational potential energy. And you got the idea that in order for there to be a potential energy it needs to be part of a system or an interaction between two objects, like gravitational potential energy was the energy stored between an object and the Earth due to its position. Something similar is going to happen here, but I want to give you a little bit of introduction. First, we'll give you a couple of just kind of conceptual ideas so that you can see what's going on here. And then we'll take some time to try to go through and work through one quick example. All right? So I've got here my friend Boba Fett, Potato Fett, and he is hanging by a spring here. All right? Now, if I pull him down just a little bit, we would say he's at his lowest point. So we could say that the Potato Fett Earth system has its lowest gravitational potential energy there. He has zero kinetic energy there. And yet, when I release him, he does two things. Number one, when I release him, he goes up, right? And number two, he starts to speed up. He actually increases his speed and therefore his kinetic energy. Now, just like before, there's a couple of different ways that we can look at this. One of those ways is that we can look at the spring as being an external force, right? I pull him down. Right now, the forces are balanced. And when I release, the spring pulls up on him, right? Initially. And then he kind of bounces up and down. We'll get to that at some other point in time. But the spring pulls up on him, therefore the spring is an external force that does work, therefore it causes him to gain energy. He's moving up, the spring is pulling up, therefore he will gain energy as he goes up. That is a positive amount of work. Now, that explains why he gains gravitational potential energy in the potato Earth system. It also could explain why he gains kinetic energy. Okay, but there's another way to look at this. Okay. When we have something that is stretched out or compressed and that is trying to get back to where it was before, we say that that and the object as a system have what we call elastic potential energy. And so there's some energy that's stored in the spring due to the fact that it's supposed to be here. This is its normal equilibrium. And because we've changed it from here down to there, we've increase that distance a little bit. That change in distance, because of the way that the spring works, causes the spring potato system to have some elastic potential energy. Now, if we include both the potato Fett and the spring and the Earth, then we are now allowed to have both elastic potential energy and gravitational potential energy. All right? All of those things will be involved in a problem like this. Okay? Once again, we pull him down. There's some energy stored here. As we release, that elastic potential energy turns into more gravitational potential energy as he goes up, and kinetic energy as he starts to speed up. Now, at some point, yes, the spring is going to compress, and the spring is actually going to start pushing downwards and cause him to slow down a little bit. But for now, that's enough. Let me show you another example of where we see this. All right? Join me at my bathroom scale. All right, so you can see the scale there. When I stand on the scale, okay, you can see that it gives some type of mass. Now, this is obviously not correct, but that's not the point. It does give a value. But if I step off quickly, watch what happens to the measure there, right? It doesn't go straight back to zero. Right? Watch this again. And we see it actually when I get on as well. When I get on, there's a little bit of wiggle there. Okay, but again, it's reading almost 55 right now. And then when I step off, you can see that there's some wiggling there. It goes back and forth. That's because the bathroom scale has in it a spring. And when you're standing on it, then that spring has been compressed. And just like with Potato Fett over here, when Potato Fett stretched the spring, it stored some energy in the spring. Same thing when I compress the spring. When I stand on top of the scale, it squashes the spring a little bit and it stores some energy inside that spring. So if I jump off real quick, that elastic potential energy that has been stored there is turned back into kinetic energy, which is the motion, and it goes back and forth until the friction inside is able to take all of that energy away. All right, so we got a couple of different situations. One with potato fed, where stretching the spring causes them to gain some energy. And then we've got the bathroom scale, where compressing the spring causes it to gain some elastic potential energy. All right, conceptually, that's the big idea here. All right, now this brings us down to some mathematics. We've got the concepts down now. Let's put the math with it, just like we did with the kinetic energy and the gravitational potential energy. All right, in this situation, we have the elastic potential energy, which is shown as 1/2 kx squared. And the 1/2 obviously is just 1/2. The k is what's called the spring constant, and it shows kind of the stiffness of the spring. The more stiff it is, the better able it is to store energy there, because it's harder to compress it, so therefore it stores the energy a little bit better. And then the x squared here is the distance of the stretch or compression. So it's not the length of the string, it's not how far it is from the beginning of the spring to the end of the spring, it's just from that equilibrium position, how far have we stretched it? Or when I push on the scale, how far down has it compressed, right? Just that distance of stretch or compression. All right, now I'm going to show that to you in an example right here. We are going to do one calculation example real quick. So we've got a block that's going on a horizontal frictionless surface, so no energy loss there. It's moving along with the speed of 1.5 meters per second, and it's got a mass of 1.2 kilograms. It's going to run into this spring over here, which is connected to the wall, and as it hits the spring, it's going to compress the spring, and the spring's going to exert a force on it, causing it to slow down, and eventually at some point, it's going to stop. Now, the spring will probably push back out and it'll start moving again, but what I'm interested in is how far is the spring going to compress when this block runs into it. That's what we're going to do. All right, so the first thing we want to do, very similar to what you've been doing with your roller coasters and drop rides and things like that, is we want to start with how much energy do we have in the beginning. All right, now we said that it was sliding along a frictionless surface. We are dealing with the mass spring system, and so we are going to have some potential energy when those two things interact. All right, so let's just look at it this way. Do we have kinetic energy? Do we have gravitational potential energy? And do we have elastic potential energy? Well, initially, yes, we've got kinetic energy, right? We can calculate that by doing 1/2 times the mass, which was 1.2, times the velocity, which is 1.5 squared, right? 1/2 mv squared. And when you put that in, you should get 1.35 joules. All right, 1.35 joules. Now, in the beginning, it doesn't have any gravitational potential energy because it's already right on the surface. It's not going to drop any further. It can't really, so we're going to go ahead and just define that as 0 height, and therefore it's not going to have gravitational potential energy. Gravitational potential energy would be 0. All right. Now, at this first point, it doesn't have elastic potential energy either, because at this point it's not interacting with the spring, and so therefore the block spring system does not have any energy stored up there. And so again, we'll say 0 for that, because the spring has not been stretched or compressed. All right. Then we move on to the final point. The block is going to come over, it's going to compress the spring, and it's going to squash it, right? So now the question is, do we have kinetic, do we have gravitational potential, and do we have elastic potential? Well, again, kinetic energy, when it comes in and compresses, the block is going to stop. And if it stops, it won't have any kinetic energy. Gravitational potential, also 0, because it's still on the surface. It hasn't gone up or down. It won't be going up or down. So therefore, the height is still 0. Last of all, we have the elastic potential. Now, if the block has hit the spring, it's going to compress that spring. It's going to squash it. And so our elastic potential here is going to be 1/2 times k, which it gives me that k, the spring constant here, is 100. Note that it is in SI units, newtons per meter. And then times x squared. but I don't know what x is. That's what I'm looking for. How far does it compress? All right. So now we've got that. We know that because there's no friction, there's no energy being lost from my system. So whatever energy I start with should be equal to the energy I end up with. In other words, I can take that 1.35 joules that I have at the beginning, and that should be equal to the 1/2 times the 100 times the x squared, because that's the only energy it had in the beginning, and that's the only type of energy it has at the end. And now we can solve for x. So you're going to divide by that 1/2, you'll divide by the 100, and then you'll be left with 0.027, and then we'll take the square root, and we get 0.164. Now remember, this is in SI units, therefore the 0.164 is 0.164 meters, which in other words is about 16.4 centimeters. So that's how far we would expect that specific spring to compress. All right, so hopefully that makes sense, both the idea that we can store energy in a spring by compressing it or stretching it, and secondly, that we can find out how much energy is there by using this formula, the 1/2 kx squared. Now, as we go through, we may find some questions that have elastic potential energy and gravitational potential energy together, but we'll see those as they come to us, and hopefully this introduction is helpful for you. All right, see you next time.